So last time I gave a brief description of what went into the proof of this holomorphic QE, and in particular I kind of mentioned how there was this thing which I call weak subconvexity, which gives some bounds for central values of L functions, which almost works, and then there's this complementary method through Poincare series and Eisenstein series due to Holowinsky, which works in a completely different case, and if you put them together, you get the whole result. So I want to give now some details of the proofs of these results. I'm not going to give a lot of details, but I want to kind of explain where the main input comes from, and it's from a very classical topic. It's about trying to understand mean values of multiplicative functions. And both results kind of use very much the fact that the Hecke eigenvalues that we have are multiplicative. So the lambda fm, lambda fn is lambda fmn, at least if m and n are coprime. And of course, if they have some common factor, then we have this slightly more complicated Hecke relation to write down. Actually, the Hecke relations are also useful, but not quite in this for what I have to say today. So let me begin with a very simple example. So which is due to Elliott, Moreno, and Shahidi. I kind of mentioned this from the mid 80s, and I explained this a little bit last time, and this has to do with is to prove a bound for Ramanujan's tau function. So the absolute value of the tau function is bounded by something like x over log x to the 1/18th, something like that. That it's a little bit smaller than x. So I have to say that my tau n is going to be the usual tau n divided by n to the 11 over 2, so that it's normalized to be of size a constant, like a divisor function. Okay. So why is this true? Well, so what I have here is a non-negative multiplicative function. And I can ask a little bit more generally, what do I expect for the sum n up to x of a non-negative multiplicative function f? So now my f is no longer going to refer to this Hecke eigenform. It's just f is some multiplicative function with f of n always being non-negative. Okay. Well, what would we like to say? Well, let me do in a general case, let me do a calculation which really doesn't make sense, but we can kind of pretend that it does. One thing I can do is I can write f of n as a sum over the divisors of n of some other multiplicative function g of d. And then if I try to look at the sum n up to x fn, I interchange the sum over d. That's the sum over d up to x, g of d, integer part of x over d, which I can pretend, if I ignore error terms, I can say that this is roughly x over d, g of d, d up to x. And now let me pretend that I extend the sum over d to infinity, so I can think of this as being roughly x times the sum over all d, which would give me some product over all primes p, 1 plus g of p over p plus, etc. Okay, maybe I should say p up to x, let's say. Okay. And now g of p is just f of p minus 1 from this relation. So what I might expect this to be, if I take the minus 1 over p outside by Mertens theorem, then this is something like x over log x times the product of 1 plus fp over p, etc. And this you can think of roughly as something like x over log x times the average value of the sum fn over n. Okay, so not a single line is correct after the first one, but it's or maybe it's not even visible. Okay, all right, but this is some kind of rough expectation. Maybe you should think of this guy as being the rough expectation, that you have some idea of what the average of a multiplicative function should be. It should converge to this product, and in many cases it would. If fn is the function which is 1 always, then g would be 0, and then that's an identity which you can check. However, there are cases where it's not so easy to prove. If fn is the Möbius function, right, so then g would be the function which is -2 on the primes. Then you're trying to show that there's cancellation in the Möbius function when you sum up to x. That's not an easy thing to prove. We know that it's true, but it's certainly not going to be asymptotic to this Euler product, so you have to be a little bit careful. There are other situations which will happen, which I'll bring up in a minute. Not quite a minute. Okay. Then, of course, there are also error terms to be considered. Okay, but at least if f is non-negative and f of p is bounded by some constant k, and f of p squared, etc., are a little bit tame, not too wild, or well behaved, let's say, then I can prove that this expectation that I have, I can prove that an upper bound of this type holds. Okay. So this is a very simple argument, so I can give it to you. So I want to look at the sum of n up to x, f of n, and let's say I multiply it by log x. If n goes up to x, there's not a whole lot of difference between log n and log x, because most numbers n around size x are close to x. They are between x over 1,000,000 and x. So this is roughly the same as the sum of n up to x, f of n log n. Now log n I can write as the sum over the primes dividing n of log p. There might be prime squares, etc., but let's not worry about that. All numbers are square free, let's say. So now if you interchange the sum over primes and integers, so what we are looking at is something like a sum over n is p times some number m, let's say. So it's m goes up to x, f of m, and then a sum over p goes up to x over m, f of p log p. Now, if f is bounded, then I can estimate the sum over p. That's just x over m. So this is bounded by whatever constant k I had times x times the sum of m up to x, fm over m. Okay. So this is kind of a very simple, almost trivial argument, but it's actually quite a useful thing. But one thing you should note is that there is this thing that I assumed here, that the values of f at the primes was bounded. And this is, if you like, this is one of the examples of where the Ramanujan condition comes in. Knowing that the Hecke eigenvalues are bounded at the primes is important, because it fits into this kind of framework. If I didn't know any kind of bound on the primes, I couldn't hope to get a result like this. It could be that f is 0 everywhere, except that you pick your one prime p, make it essentially infinite if you like, and then you're not going to get any inequality of this type. Okay. Of course, you can kind of make more refined versions of this. If you had a version of this in greater generality, escape of mass would have been a very easy thing to prove. I haven't said much about this escape of mass argument, but really what I was trying to do in that paper was to make some version of this hold when you don't have the Ramanujan conjecture, and that takes some effort to do. Okay, so now let me return to the absolute value of tau n. And you can see that fits nicely into this. The tau p's are less than 2 in size. So I immediately get that the sum n up to x tau n is bounded in size by some constant x over log x times the product over p, 1 plus tau p over p plus so on. Which, if you like, we can write as x times the exponential of the primes up to x, absolute value of tau p, minus 1 over p. So you will recall that the Holowinsky bounds that I discussed had expressions which were somewhat similar to this. Okay, then how do you bound this? I said that you could use Sato-Tate. You're trying to understand whether the tau p's could always be close to 1. If they're not close to 1, you should get some cancellation. But you can do the same thing with just knowing something about Rankin-Selberg and knowing something about the Rankin-Selberg of the symmetric square. So what do we know? I know that the sum over p up to x, tau p squared over p, that's the Rankin-Selberg of the Ramanujan delta function. So that will be asymptotic to log x, basically the sum of 1 over p up to x. Then I also know that the symmetric square function associated to tau would have coefficients which are tau p squared, which is tau of p squared minus 1. This is an object which we know comes from something on GL3, so you can do Rankin-Selberg on that. So I have another expression which looks like this. Tau p squared minus 1 squared over p is asymptotic to log x also. Okay. And this is very useful because, okay, maybe. And that last expression is very useful because what it says is that the sum p up to x of absolute value of tau p minus 1 squared times absolute value of tau p plus 1 squared, the product of those just gives me tau p squared minus 1 over p is about log x. Well, this guy is at most 3. Again, I'm using Ramanujan, so this is at most 9. And so I conclude that the sum over p up to x mod tau p squared over p is at least a ninth of log x. Okay. Then if I expand this out, that's just the average of 1 over p, which is log x, the average of tau p squared over p, which gives me another log x, that's 2 log x, and then the cross terms is minus twice what I want, the sum p up to x, tau p over p. Okay. So if I rewrite this, then I see exactly what I want, that the sum p up to x, tau p minus 1 over p is less than minus 1 over 18 log x. Okay. And if I plug that into my estimate here, I have shown for you that the average value of tau n is a little bit smaller than 1. So it's a fairly straightforward argument. So this tells you why these Hecke eigenvalues you should expect to be small. The key input there was to know something about, say, the symmetric square L function that was automorphic, and so you could do basically the symmetric fourth power of tau. Okay. If you had more information, you would get better values for this constant. All right. So now let me say quickly what Holowinsky's argument is. Not too much about this. So you can see again that in that argument, I had to make use of the Ramanujan conjecture fairly strongly. So this will also use the Ramanujan conjecture. So again, we're going to use the fact that lambda f is a multiplicative function. And it's because this is multiplicative that if you want to understand something about the sum n up to x of lambda f n times lambda f n plus 1, so if I had the inner product with Poincare series, I would have had a lambda f n times lambda f n plus m, and this x would be something like k, essentially the weight of the form. And what you have to use is that the multiplicative relation of the fact that these are multiplicative, how do I want to say it? I want to say that the multiplicative structure of n is completely different from the multiplicative structure of n plus 1 or n plus m for any small value of n. Another way to think about it is that I'm evaluating now a function, these Hecke eigenvalues at a number which is of the form n times n plus 1. Okay, the numbers n times n plus 1 are very special numbers up to x. One way to see it is that a number up to x typically has about log x prime factors. And a number up to x squared will also have log of x squared prime factors, which is the same as log x. Log doesn't change much. But if you take a number which is of the form n times n plus 1, that will tend to have twice log x prime factors. N has log x prime factors. N plus 1 will also have log x prime factors. So you're evaluating this function on a very special class of numbers. Now, this argument kind of says that on average, your Hecke eigenvalues are small at primes. That kind of builds up. So when you multiply a whole bunch of primes together, you're getting that the average value of tau n is small. So you're going to get twice the result here because you're multiplying twice as many prime factors as you would in the case of just something like summing tau n up to x. You can make that precise. So this is a bound which I said yes last time. It comes out of sieve methods. Originally, it was considered by Nair, who proved very general bounds of this type, again, for a general multiplicative function which was non-negative and which was bounded by something on the primes. So it's Nair's result, if you like, is kind of it's a generalization of results like this, where instead of evaluating a multiplicative function on the integers, you evaluate it at the values of a polynomial. The polynomial could be reducible, could be irreducible, and he gives you an explicit bound for these. So in this case, you have a reducible quadratic polynomial that you're evaluating on, and you would get that this was bounded by okay. So it's very important in this argument also that the function f lambda f that you consider should satisfy the Ramanujan hypothesis. So why is that? Usually, when we are trying to use sieve methods, we can understand what happens with all the small primes. If you look at only the primes up to x to the 1 over 100, you can kind of figure out how often a prime less than x to the 1 over 100 divides this, how often it divides that, and also what all the correlations among them are. Okay. Once the primes start getting larger, you lose control over it. Like if you want to know, maybe you could still do it in this case, but in principle, if you had a very large prime, you would have a hard time figuring out, how many primes larger than n to the 99 over 100 divide this or divide that. Not strictly speaking true, but okay, roughly that's the point. So what you would like to do is, among these numbers, you would like to keep only the prime factors which are small and ignore all the prime factors that are large. If you can do that, you're in good shape and you can make this sub-argument work. Why can you do that? Well, how many prime factors can a number have which are larger than n to the 1 over 100? No more than 100 of them. And the lambda p's are all bounded by 2. So you just throw away all those primes. There are at most 100 guys that you will forget. Each one of them is less than 2. So you'll be off by something like 2 to the 100, but that's just a constant which I observe here. Okay? So the idea here is that can ignore all large primes because of Ramanujan. Okay, so the moral is that in several aspects of this analysis, you use very crucially the fact that you have the Ramanujan conjectures, which is very different from the ergodic theory approach where the Ramanujan condition is somehow completely irrelevant. You don't care whether your Hecke eigenvalues are large or small. If they are large, even better, you have more entropy if you have really large Hecke eigenvalues. Okay, so and then, once you're there, you just plug in the same estimate here, that the easy bound that we derived, and then you get Holovinsky's bound that I stated before. So now I want to say something about the other approach, the idea towards weak subconvexity, which also relies on something to do with multiplicative functions. So I never really told you what the convexity bound was. I kind of said it several times, but I didn't write it down properly. So you could look at the notes where I give a proper definition of what the conductor should be in terms of the parameters that appear in the functional equation of an L function. So the simplest thing, if you want to keep in mind, might be something like, say you look at a Dirichlet L function Ls chi mod q is a character, and it has some functional equation which would look like q over pi to the s over 2 gamma of s over 2, at least if this is an even character, equals the same thing at 1 minus s. Now, and the conductor here would have been, so if I want to evaluate this at half, then I would think of the conductor as being q. What does this mean, this conductor being q? It means that you can write an expression for L half chi. So the Dirichlet series defining Ls chi, in fact, will converge conditionally even to the right of 0. But you can kind of approximate Ls chi by taking a sum of the character values up to square root of q plus some other number which is of size 1. It's like a Gauss sum times the sum over, again, n up to square root of q, chi bar n over square root of n. Now this is called the approximate functional equation. And what it means is that you can approximate any L function that you want at some point, let's say on the critical line, by 2 terms. The length of these terms would be of size square root of the conductor. So for the zeta function at half plus it, you should think of the conductor as being of size t, and then you can write zeta of half plus it as a sum of 2 terms, both of which will go up towards square root of t. If you have an expression like this, you can see why the convexity bound would be the conductor to the 1/4, because if you just put absolute values everywhere, you know nothing about the cancellation of the character sums chi n. If you replace them all by 1, then you would get a sum over n up to square root of q over 1 over square root of n, which gives me a q to the 1/4. So the trivial bound is q to the 1/4 in this case. So that's kind of the general principle for any L function. You can approximate any L value that you want at half by a Dirichlet series which goes up to, by a truncation of its Dirichlet series, going up to about square root of the conductor terms. And now it's no longer so clear that you can take a trivial estimate because, well, maybe you have to assume Ramanujan, maybe your coefficients grow like divisor functions instead of being bounded by 1. But anyway, you can bound it by something like conductor to the 1/4 plus an epsilon usually, but you can get rid of the epsilon. Okay, so this is called the trivial bound, but it's not really trivial. It takes some proof. In generality, it was done only in the about 10 years back by Molteni. Now, and recently Heath Brown has a very nice proof of it, which really gives conductor to the 1/4 without epsilon. Okay. Now, in the case of Dirichlet L functions, you can see that if I understood something about the character sums n up to x chi n, so if I know cancellation in here, for values of x which are a little bit smaller than q to the 1/2 minus delta. So here I should say, cancellation kind of means a robust kind of cancellation, not just that it's little o of x, but maybe if you know that it grows like x to the 1 minus delta for some delta that's positive. Okay? If you know that, then you can see that I can plug in bounds like that here, and then I would get a subconvexity bound. So that would imply a subconvexity bound. For L half chi. And this is the kind of thing that was done in the 50s and 60s. Burgess showed that you have cancellation in sums like this when x is bigger than q to the 1/4 plus epsilon. And the methods that he used to prove this would imply some subconvexity bound for, so this is not quite an imply, but the same techniques imply that you get some bound for L half chi like q to the 3/16. 3/16 is less than 4/16, which is the convexity bound. Now, conversely, if you start with a convexity bound, that can be used to show that if you look at the sum n up to x chi n has cancellation for x bigger than, a little bit larger than the square root of the conductor. Okay. This is an easy thing. You can use Perron's formula or something to write this as an integral of the L function times x to the s over s ds on some line. You move the line of integration to the half line, and then plug in whatever bounds you have for the L functions on the half line. So this is and then move this to the half line. Something like that. Okay, so at least in principle, this convexity bound is kind of connected to cancellations in the sums of the Fourier coefficients of your L functions, the Dirichlet series coefficients. You have cancellation around the size of square root of the conductor, and you would like to know that there's cancellation a little bit below square root of the conductor. Okay. There are other ways of proving this convexity bound. Okay, so there are other ways of proving this convexity bound. One way is to just use the functional equation and use Fragment-Lindelof. You can evaluate this L function just to the right of 1, and by the functional equation you can evaluate it to the left of 0, and then Fragment-Lindelof will give you some bound for this on the half line, and you can calculate a bound using Stirling's formula. Okay, so that's the setup. So now let me explain how this weak subconvexity goes. So I'm interested in some L function which I will denote by something like L half pi. This pi is not pi from pi day, but okay, maybe it corresponds to some automorphic representation, whatever that means. So this has some Dirichlet series a pi n over n to the s, and it has some Euler product. And I'm going to assume that it has some functional equation. So you multiply by some gamma factors, and then there's a relation which connects this to L1 minus S of pi conjugate, basically, which most of our L functions will satisfy. And I have to assume some analog of the Ramanujan conjecture, so I'm going to call this the weak Ramanujan conjecture. Which says something like, I can bound the values of a pi p squared, say with a log p over p, on average in dyadic intervals, so between 2 to the L and 2 to the L plus 1, that this is bounded by some constant. Okay. So if the coefficients are bounded at the primes, then that would be the Ramanujan conjecture, and then this would be satisfied. You just sum log p over p in a dyadic interval, that would be satisfied. But this gives me a little bit extra flexibility because I want to make an application of this to the function f times a mass form phi j. Now, f was a holomorphic Hecker eigenform which satisfied the Ramanujan conjecture, but the mass form phi j may not satisfy the Ramanujan conjecture. I want to cover that possibility, so I input some condition like this. If phi j is fixed, I can check this by Rankin-Selberg for phi j. Okay, that's the advantage. So under these circumstances, weak subconvexity would say that I have a bound for L half pi, which is like conductor to the 1/4 divided by log of the conductor to the 1 minus epsilon. And what we know is some kind of convexity bound, which is that it's bounded by conductor to the 1/4. Okay. So how do we save this extra log? So I began by saying that the convexity bound implies that there's cancellation of these coefficients an at some point. So we know that if I look at the sum n up to x a pi n, that this is a little bit small. Say it's smaller than x over log x, provided x is a little bit bigger than the square root of the conductor, so square root of the conductor times maybe log conductor to the million, let's say. So this you can get from convexity. Now, I'll try to explain why, if you have a bound like this, then this actually implies that the sum n up to x a pi n is again bounded by x over log x to the, well, maybe you lose an epsilon, 1 minus epsilon, provided x is bigger than square root of c divided by log c to the million. Okay. So this is kind of a purely formal statement about mean values of multiplicative functions, that once I know that they are small from some point onwards, I can actually kind of extrapolate and get them to be small a little bit before what I need. Okay, so why is this true? So what am I trying to say? I'm trying to say something like this. Let me draw a graph of the mean values of a multiplicative function. It's doing something initially, whatever it's doing, and I know that from some point onwards it's actually pretty close to 0. Right? This is at the square root of the conductor. And what I want to say is that it can't just go from here to there, like it can't remain big all the way up here and then suddenly drop down to 0. It has to kind of go down to 0 in some continuous way. Okay? So this is some kind of a continuity principle. Now, of course, if you just sum some random numbers up to x and you know that they cancel out somewhere, there's no reason to expect that they're going to cancel out anywhere before that. I mean, why should they? You know nothing about what happened until you get to the point of cancellation. What makes these numbers a pi n not random is that they are multiplicative. So I want to say that if you have a multiplicative function which cancels out at some point, then it has to cancel out a little bit before you got to that point. Okay, why is that true? This is a feature of mean values of multiplicative functions. And the principle would be that they vary very slowly. So maybe, to get a quick sense, you can think of your favorite multiplicative function, like if you say you take the divisor function n up to x dn, then that's kind of asymptotic to log x, and you can kind of see that the log x is varying slowly, right? So if you take this average at x and you take the average at 2x and you subtract, that difference is going to be small in a certain sense. Okay, let me explain more carefully what this means. So let me tell you some of the reasons behind this. So to give you an historical problem, so imagine that you have a multiplicative function f, and it's just some nice real valued function which takes values between -1 and 1. And I ask you the following question, which is due to Erdős and Wintner. Does this limit exist? Okay. So you can see that this is not such an easy question, because I can just take fn to be the Möbius function, and then knowing that the limit exists for the Möbius function is exactly the same statement as knowing the prime number theorem. Okay. So it's a statement which has some content that if you want to show that this limit exists, and it was first proved by Wörsing. So I have kind of two lines to say on what Wörsing did. This was proved in the late 60s by Wörsing. What he did was, along the lines of what I explained in the case of tau n, you look at the sum n up to x fn, you multiply it by a log n, which, as I said, is roughly the same as taking log x and multiplying it by the sum n up to x fn. And then you rewrite this in terms of primes, and you interchange, so you get that this side will be roughly the sum over the primes up to x, f of p log p, times the sum over m up to x over p of f of m. So if you like, I can write this in the following way. If I take the average value of this multiplicative function at x, so I have to put a 1 over x here, which I can write as the average value up to x over p, and then there'll be a p here, something like that. So what does this mean? This means that the average value of the multiplicative function at x is some kind of an average of the average values of the multiplicative functions until x. So the average of f at x is some kind of an average of averages up to x over p. The sum of log p over p is just a log x, so this guy also behaves like some kind of an average. So in other words, whatever this thing that we are studying, it's not just the value of some function at a point. Each value of the function at a point is an average of all the values which came before it. So of course, if it's an average of things which happened before it, it can't be some very very non-smooth function, it has to have at least some continuity properties because it is some kind of integral of things that went past it. So you can write this as some kind of a convolution equation. So the convolution equation just formally would be something like the value of the function at some point is the convolution of some other function which is telling you what happens on the primes. Let's call it chi, convolved with the function sigma. So basically it's things which solve some kind of integral equation of this type. Okay, and this integral equation means that it's not as coarse as you might think it would be. Okay, and he was able to give a proof based on this that that if you start out by having some mean value which is getting small, then it's going to keep getting smaller and smaller as you go on, and the limit would exist. And various ideas of this proof, you can kind of see some versions of this also in the elementary proof of the prime number theorem by Selberg and Erdős. So that has ideas which are closely related to this. Now, okay, so what? Well, let me generalize the problem a bit, and I ask about if I have a complex valued multiplicative function f, and with mod f less than 1, restricted to the unit circle, then I can ask the same question, does this limit n up to x fn, does this limit exist? Now here you can see that the answer is no, and you have a very simple example. You can take fn to be n to the I alpha, which is certainly nice and multiplicative, for some real number alpha, not equal to 0. And then, of course, we can work out what the sum n up to x, n to the I alpha looks like. That's basically x to the 1 plus I alpha over 1 plus I alpha. And so the limit doesn't exist, it's going to just oscillate. So Halas realized that this is basically the only example that you have. And what you can prove is that if f doesn't look like n to the I alpha for some alpha, maybe 0, maybe non-zero, then the limit exists and is 0. Okay, so I have to say, what does it mean for a function to look like n to the I alpha? It's a multiplicative function, so I only want to say that f of p should look like p to the I alpha for prime numbers p. And one way I can quantify that is to consider the sum something like 1 minus f of p divided by p to the minus I alpha. So if f looks like that, then this should be close to 1. Maybe I take the real part of that, not so important, but okay, so let's take the real part of that, divided by p. And I want to say that this, that if this converges for some alpha. So if it converges for some alpha, then I would say that f of p looks like p to the I alpha, right? And in that case, the limit doesn't exist. If it diverges for every alpha, then the limit exists and is equal to 0. I can leave it to you as an exercise that if you take two different values, alpha and beta, the sum can't converge for two different values. If it converges for a unique value of alpha. That's easy to see because p to the I alpha can't look like p to the I beta for some different values, alpha and beta. Now, once you think of these principles, you can ask the following question, which is heading towards this weak subconvexity that I want to give some idea about. Let's think about how the mean values of a multiplicative function should oscillate. So again, let's just think of a complex valued multiplicative function with mod fn less than 1. So I want to sort of compare the mean value at some point x. And I want to say if there's some relation between this and the mean value at some nearby point x over y. So y might be like x to the 0.001, and I want to say that these numbers are kind of close to each other. Well, of course, they need not be close to each other. If f looks like n to the I alpha, if I take the mean value at x, it would have x to the I alpha over 1 plus I alpha. The other guy would have x over y to the I alpha. So they might be a little bit off. One thing you can see is that if I take absolute values, they're going to be actually close to each other even in that case. So here's a result which is true. If you take the absolute value here and you take the difference from this, the size of that difference is bounded by something like log y over log x to the 1 over 20 or something, with some constants. So if y is a very, very small power of x, then there's not much difference between the mean value of your multiplicative function at x and the mean value of the multiplicative function at x over y. So this is going along the lines that I want. I know that there's cancellation in my sum at square root of the conductor times some powers of log. I want to extrapolate it to a little bit smaller than square root of x times square root of the conductor times the power of log. If I had a result like this, then that would be plenty good. So of course, so this result is due to Elliott. And you can kind of make a more precise version of this result by saying that both of these guys are small, unless you're in this case of Hallis's theorem where the function is pretending to be n to the I alpha, and then you can kind of make a more precise statement of how the functions actually vary. What's in the less than here? Oh, but this is a constant of the exponent here, right? So this constant might be some constant like 10 to the 10, let's say, maybe 10 to the 10. I mean, I can work out explicitly what it is. It's just a constant. Ah, but y could be, so okay, but y could be, y could be log x to the 100. It's still a non-trivial theorem there, and then and then it's some power of log. Right? But if this is, with this thing, you still have a result if y is, x to the 1 over 10 to the 10 to the 10 to the 10. Right? So it gives a non-trivial statement there. So, okay. Now, so now what happens if f is no longer inside the unit circle? But I am going to assume some kind of Ramanujan type condition that f of p is basically bounded, or at least on average. So you can have more complicated situations here. The simplest thing is to think of, say, you think of the k divisor function dkn, and then if you average, so I know that the sum n up to x of dkn, so k is some integer, that this is asymptotic to some polynomial in log x of degree k minus 1. So it's a routine calculation that you do this. So now if you take the difference between this mean value at x and the mean value at x over y, you kind of knock off the leading power of log. Instead of getting log x to the k minus 1, you would get log x to the k minus 2. But you can't say that the mean values are kind of close to each other. You can just say that they're a little bit smaller than what they were before. Okay? But you can do something more clever. Say if you say if I have k equals 2, instead of just taking the mean value at x and the mean value at x over y, I can do something like take the mean value at x and subtract 2 times the mean value at x over y, and then add back 1 times the mean value at x over y squared. Okay, so it's kind of like taking a a second derivative of this degree 1 polynomial instead of taking a first derivative. If I take the second derivative of degree 1 polynomial, I get 0. Okay, so now I can say that this linear combination is actually going to be small, instead of saying that just comparing the two mean values is small. And for a general k, I could write down a linear combination of mean values at x, x over y squared, up to x over y to the k. And then I would be able to say that the linear combination at these values is actually small. So there's kind of no mystery about what this linear combination should be. So let me maybe show you what it should be. I'm trying to deal with the function, the k divisor function, which is something like zeta of s to the k. I'm trying to evaluate something in terms of this. If I multiply this by x to the s ds over s, that's kind of counting for me on some line like 2 minus I infinity, 2 plus I infinity. That's counting for me the number of divisors, number of k divisors up to x. Okay. So what is the problem? The problem is that I pick up various powers of log because zeta of s at s equals 1 has a pole of order k. I would like to kill this pole of order k. What should I do? I can multiply it by some function which is going to have a 0 of order k at 1. So here's my example of a function which has a 0 of order k, something like 1 minus y to the s minus 1 to the power k. All right? Maybe I should put this with a plus 1 and a minus s here. Doesn't matter. Now, what happens when I expand this out? What I get from the one term, I would get the sum of the function up to x. And then from these various other things, I would get minus, k choose 1 times the sum of the functions at x, y, plus k choose 2 times the sum of the functions at x over y squared, etc., etc. By just expanding this out using the binomial theorem. That's my linear combination. So I've constructed for you a linear combination of these mean values. And since I've killed all these poles, I can now move the line of integration to the left. And I conclude that this linear combination is small. Okay. Of course, this is just in this particular example. Right? Now, we could have a more complicated example. So here's the more complicated example. It's kind of along the lines of Hallas's theorem, where your function could look like n to the I alpha for some alpha. So now it could look like n to the I alpha for several different values of alpha. So maybe your function looks like your generating function of fn over n to the s. Maybe it looks like zeta of s plus I alpha 1 to some power k1, zeta of s plus I alpha 2 to the k2, etc., etc. Some finitely many such objects, right? So if you compute the mean value of this, you will pick up some contribution of a pole at 1 minus I alpha 1, 1 minus I alpha 2, etc. You'll get some polynomial type thing in log x. It'll be a bit of a mess, but you can compute it. So I want to do the same kind of calculation. I'm trying to look at this integral of this generating function. X to the s over s ds. This will count for me the mean value of this function up to x. And again, what I would like to do is to find something which is going to kill all the poles at 1 minus I alpha 1, 1 minus I alpha 2, etc. So I kind of generalize what I did before. I will multiply it by 1 minus y to the 1 minus I alpha 1 minus s to the k1, 1 minus y to the 1 minus I alpha 2 minus S to the K2, and so on. So this is some object which I can now move lines of integration and show that this is small. But at the same time, if I expand this out using the binomial theorem and figure out what I'm doing, what I get is that I get a linear combination, that the right-hand side is going to be a linear combination of the mean values at x, x over y squared, all the way up to x over y to the k1 plus k2 up to kr. So the game is going to be that I'm going to construct some linear combination of these, some non-trivial linear combination of the mean values of these points, and show that that's going to be small. Okay. So it turns out that a general multiplicative function, which is kind of bounded, doesn't look any worse than this example that I've given here. So there are kind of a couple of things to be done. One is that, so you start with your general multiplicative function f of s, with fp's bounded, basically. So you look at the generating function f of 1 plus, say, 1 over log x plus it for some small value of t. Maybe t goes up to some log x to the 100. It's not so important what these things are. They're fairly tame, and you can have a number of ways of choosing them. So what do these numbers alpha 1, alpha 2 mean? They are the points where your generating function is very large, because the zeta function has a pole at 1 minus I alpha 1, 1 minus I alpha 2, etc. Here, this generating function. So what I should do is I kind of look at this function on this big region and pick out the point where it's largest. Okay. And then I throw away a small region around it. And then I pick out the point where it's second largest, throw away a small region around it, and then pick out the third largest, etc. So that's the construction which is going to tell me what these numbers alpha 1 to alpha r are. So these I call successive maxima. And I explain precisely how these small intervals are defined in the notes. Once you do this, the nice feature is that the successive maxima keep getting smaller. And if you take away a constant number of them, like if you remove something like k square or k cube successive maxima, then you basically kind of figured out everything you want to know about your function f. You've isolated all the points where it's large, and whatever is left over is going to be uniformly small on the whole interval. Okay, so you do that, and then you have the exact same thing. So once you've figured out what the successive maxima are, you kill the function near the successive maxima by multiplying by some terms like this, which will vanish at the successive maxima. You raise them to a sufficiently high power so that the function is then going to get small. So you do that, and you use Halas's method. So kill the function at and use Halas. And then what you're led to is that there will be, so what you would prove is that there exists a linear combination of your multiplicative function at x over y squared, and so on up to x over y to some large number k, depending on what the bound for your multiplicative function are and how good an answer that you want, which is small. So the average, so this is a linear combination of the averages at these points, and you can prove that that's smaller than 1 over log x or something like that, to the 1 minus epsilon. So now I'm almost done. So I take my function, my L function for which I want to prove a weak subconvexity bound. What I know is that if I take the sum n up to x, a pi n, I know that there's cancellation for x bigger than square root of the conductor times log of the conductor to some power million, let's say. Well, I know that there's a linear combination at these various points, which I know to be small. Now here's the point. I take y to be log x to the, let's say, 10 to the 7, 10 million, and I rig it so that x over y squared, all the way up to x over y to the k minus 1, that these are all bigger than this cutoff point, square root of c log x to the log c to the million. Okay, but the last guy, x over y to the k, is pretty small. It's like square root of c log x to the log c to the minus a million, because y is a large power of log x. Okay, I know that the linear combination of the mean values at all these points is small, but by convexity, I know that all of these mean values are small, because those all lie about where I have cancellation. And so for free, I get that there is cancellation at this point. And that's the proof. So you can make this work, and then you save one log, and that feeds into this weak subconvexity bound. Okay, so that's about all, I think. Thank you very much.